In this demonstration, we're going to look at the concept of phase changes by using the chemical compound nitrogen. We're going to look at nitrogen in two different forms, in the liquid form and the gaseous form. Most of you probably realize that in our atmosphere right now, a little under 80% of the air that you breathe is nitrogen. Only about 20% or so is actually oxygen. Both of those gases are colorless, odorless gases, so when we're looking through the air right now, we're not really seeing anything at all. However, if I get the temperature of gases cold enough, right, we can slow the molecules down enough, where the molecules will actually stick together based on the intermolecular forces. And to do that, however, to slow them down, we have to get them very, very cold. What I have in this container right here is some nitrogen from the air that has been liquefied. In order to do that, we have to get the temperature down to minus 320 degrees Fahrenheit, almost minus 200 degrees Celsius. Now what I'm going to do is I'm going to pour some into this beaker right here that we have on the tabletop. And you'll notice something happens right away. And very often when we ask someone what it appears to be doing, they'll say it's really bubbling a lot. But somewhere along the line, somebody will realize, gee, it actually looks like boiling water, like on your stove at home. And that's because it is boiling. Since it's boiling, liquefaction temperature is minus 320 Fahrenheit or around minus 200 Celsius, that's its boiling point as well. The tabletop here is about 70 degrees above 0 Fahrenheit, more than hot enough to boil it, which is exactly what we're seeing right there. Now, the other thing that we look at here, particularly against the black background of the table, you'll notice some smoke. And at first, many people think it's nitrogen. Well, the nitrogen isn't visible. It doesn't have any color. What's happening is that the gas coming off of here is so cold that as it comes off of there, even though it's boiling, it's cold enough to make the water condense from the air. Very similar to in the wintertime when you breathe out, the air in your lungs has water vapor in it, and the gas on the outside in the air is cold enough to condense the water. I'm going to have a demonstrator, Jack, come up here, and together we're going to demonstrate a few things with you. Now, one of the things that I think is a little troublesome to people is that when they see this boiling, they think that it must be hot. Now, I'm going to demonstrate this for you, Jack, and then I'm going to have you do it. And I want you to put your hand in there, but just don't touch the liquid. This is actually safe to do. Even if Jack does happen to touch the liquid, he will not do that very long. It's pretty cold. So he's just going to put it above there and describe to us what it feels like to you.
Very, very cold.
Very, very cold. You'll notice, and I'll stick my hand in, and you can see it smoking. The reason it's smoking a little bit extra is that everybody's hand is sweating. You saw Jack's do that, you saw mine do that, and so it's condensing the water from our sweat into some smoke there. Now we're going to do a couple of demonstrations for everybody that shows them how cold it is. Now the first demonstration I've actually started here, and Jack, if you'd reach for that test tube right there, that'll do it. That's perfect. Now right now the test tube has air in it. So it's about 80% nitrogen, 20% oxygen. So it looks like there's nothing in there, but of course air is. Now what I'm going to do is I already have one of the test tubes in there. I'm going to put it in there. I'm going to add a little bit more nitrogen to it because the beaker's so warm that it causes some of the nitrogen to boil away. So I'm just going to pour this in. Oxygen has a higher boiling point than nitrogen. So what we're actually going to see here is that it's going to be able to separate, it's going to be able to liquefy some of the oxygen from the air using the liquefied nitrogen. We'll look at it a little bit later. Because this keeps boiling away, I'm going to have to pour a little bit more into there like so. Now the first demonstration that Jack and I are going to do for you, first of all I'm going to move this a little bit toward me. We don't want to grab this beaker with our hand. It's very, very cold. It would probably frostbite us here. You'll see that the beaker's turning white, and that's from the water from the air forming ice, a layer of ice on it. First of all, we have this balloon right here. And the balloon is full of air. Or this one, actually, I filled this with carbon dioxide gas. So the reason the balloon is inflated is that the carbon dioxide molecules are moving around really fast in there and bouncing around and hitting the sides of the balloon, causing it to expand. We really don't know why gas molecules move, but we can do lots of experiments that show us that they do. Now we do know, even though we don't know why they move, we do know that if you heat up gas molecules, they move faster. They would hit the sides of the balloon harder, but the balloon would expand. What Jack is going to do, he's going to make them move really, really slow by holding them in the liquid nitrogen. So I want you all to think about what the balloon is going to do, and let's see if it actually does. So Jack, I'd like you to hold it like that. Gotcha. And I'm going to take your hand, and we're going to lower your, not your hand, but the balloon, of course, into the liquid, and let's see what happens. So the molecules are going to start to move slower as they cool down, slowing down, and the balloon has collapsed. But now when we take it out, they're going to start to warm up, so they're moving faster and faster and faster, so they're starting to hit the balloon harder and harder, and the balloon is simply going to come back to normal. We'll slow them down again, and then we'll just set it off to the side. So that's a great illustration of the concept of molecular speeds being tied in with temperature. All temperature really is, it's a measure of average molecular speed. And our little balloon experiment proves that. We're going to do another experiment that's really, really fun that illustrates maybe on a more dramatic scale how cold this really is. So I'm going to put some paper towels here, like so, and these are kind of to collect the mess. And I have a carnation right here. And I'd like you to feel the carnation petals, Jack, and we can feel them, and they're nice and soft. And the reason that flower petals, these carnation petals, are so soft is that the carnation petals are mostly made out of water. If you touch your skin's soft for the same reason. Your body's mostly made out of water as well. So we're bigger bags of water. These are little skinnier bags of water. Now what we're going to do is we're going to hold this into the liquid nitrogen for 3 seconds. I'm going to take it out. I'm going to hold it over the top like that, and when I tell you to clap it, Jack, right on top of the flower, okay, clap it and then let go. Don't hold it like that. You'll be kind of cold. Just clap it and let go. Now feel the flower one more time. It's not going to feel like that again. So I'm going to hold this in here. 1 1,000, 2 1,000, 3 1,000. We're getting some smoke again because of the water. The flower looks the same. And go ahead and clap it. And what did that feel like to you?
Oh my gosh, it's glass.
Yeah, that's a great description. In fact, a perfect description. It feels like really thin glass, cold, of course, as well. Yeah. So in 3 seconds, the nitrogen froze that solid. All right, and of course, what's going to happen, since we have these little parts, it's going to thaw out really quickly, and we'll have a bunch of kind of moist, limp flower petals there. Now I'm going to take one of these test tubes out. This might be a little harder to see, but we have some liquid in there. So what it has done, it's distilled some of the, condensed some of the oxygen out of the air. Now the mixture that we have there is actually about 50-50 oxygen and nitrogen. If we took that and then did the same thing, heated it up and then condensed that down again, eventually we could get the oxygen pure and pure and pure. And that's one of the principles behind fractional distillation, which is used to refine petroleum into gasoline and other products. And eventually what's going to, if we poured this out of here, it's not going to really do much. It's going to hit the table and it's going to boil immediately on there. So what we have here is an example with the liquid nitrogen rule. Right in front of us here, the nitrogen, because of the warm temperature of the room and the tabletop, is boiling. It's changing from a liquid into a gas. And that's all we got.